So, well, thank you for the invitation, and sorry everybody for the problem. They are always occurring. I have 3 computers here, and well, actually this is the problem. So, but today I'm here to talk with you about tuning isolated zero field skyrmions and spin spiral at room temperature in synthetic ferrimagnetic multilayers. So the title is really long, but we will go step by step. And something that is really important is that this work was done in collaboration from 2 groups, research group. We are in Brazil, but I'm from the University of Campinas. And there's another research group which is near us, which is part of the Brazilian synchrotron light laboratory. So, oops, I will need to put it on this. So, but first, speaking about Campinas, Campinas is the city where both of the research group are. The University of Campinas, so Unicamp, is one among the best universities in South America. Of course, we are speaking about everywhere in the world. Normally, you know more the university and the research group around yourself. But so in South America, Unicamp, the University of Campinas, only dedicated to exact science research. It was founded to do some research in exact science, and we are pretty big. More than 40,000 students and 2,000 professors. And at 2 kilometers from the campus of the university, there's the National Center for Research in Energy and Materials, which is for the group of 4 excellence laboratories founded by the government of Brazil. And one of these laboratories is the new synchrotron that we have, which is called Sirius. There was an old synchrotron, but was already the unique, only one synchrotron in Latin America. Sirius, it's at the end of the commissioning process, and it's a synchrotron of the 4th generation. So it's really competing among the other new and novel synchrotrons around the world. And so this work was done really in collaboration between the 2 research groups. My laboratory, more specifically, which is called the Laboratory of Materials and Low Temperature, we are a pretty large group with several research lines. More specifically about magnetic nanostructures, we are doing nanoparticles, more for hyperthermia, nanowires for multifunctional systems and spintronics, nanoelectronics. We are also doing some pattern 2D film, specifically spin-eyes for frustrated systems, multilayers for spintronics, which will be the talk of today. And we are also doing some novel materials through the metallic flux method in bulk and in nanowires. We are also doing some direct nanowriting by focused electron beam induced deposition. And of course, well, other common deposition technique. So today I will speak more about spintronics and in multilayers. So the objective of this project was to really directly observe individual skyrmions in ferrimagnetic multilayers. And so not ferromagnetic, not anti-ferromagnetic, but ferrimagnetic multilayers. And of course, what is really important, at room temperature and under null external magnetic field. So here, what I want to show you at the outline, so we will speak about skyrmions, a really short introduction, and then the material that we use for the ferrimagnetic multilayer, it's cobalt gadolinium. I will show you that we really have, even in small multilayers, an antiferromagnetic coupling between the cobalt and the gadolinium. And then to be able to stabilize these skyrmions at room temperature and under null external magnetic field, we used two different approaches. In one, we decide to use some lateral confinement to be able to stabilize individual skyrmions. And on the other side, we decide to vary the thickness of the ferrimagnetic multilayer until achieving a thickness where we were able to directly have this stabilization. So a quick overview of skyrmions. Of course, I will not show everything about skyrmions here, but to remember at the beginning, almost 10 years ago, more than 10 years ago, for the information storage, there was the racetrack memory. That was the idea to have the information in domain walls, codified in domain walls that will have the motion by spin current. And along the years, we saw that there was some problems of the domain wall spinning, the velocity that the domain walls were able to achieve, and so on. And so at some point, there was the idea of having a racetrack memory, but not based on domain walls, but on skyrmions. The 1 and the 0 of the bit of information will be the presence or not of a skyrmions. So we are speaking a lot about skyrmions and skyrmions. So a really quick definition, what is important is that it's a spin texture. So it's the direction of the spin of the magnetization, but has a topological protection. And this is why it has a lot of advantage compared to the domain walls, especially about the current and the velocity of propagation. And of course, it's defected. There's a defect protection. One thing that is important, but it's changing, but mostly most of the systems, I will say before, we're needing special interaction, exchange interaction. So the Dichroism-Maria interaction to be able to achieve this kind of spin texture. This interaction, what is important is that it's a non-collinear interaction. So at the end, you have an exchange between one neighbor to the other, but at the end, you have an helicoidal precession of the magnetization. And to have a system where you have this interaction, the DMI interaction, normally you should have a lack of symmetry center in the magnetic system and a strong spin-orbit coupling between the spins. You can achieve this through multi-layers or to having a heavy metal and a ferromagnetic material in contact, and then you will have an interfacial Dichroism-Maria interaction. Or in bulk, if you have an elimagnetic materials, the proper crystalline structure has a lack of symmetry, and so you can have directly in bulk. So here we will focus on multi-layers. One thing that is important about skyrmions is their chirality. So because they are the result of the competition between three energy. So of course, here we have the exchange energy, there's the magnetostatic energy through the stray field and so on. And then we have this third energy that is occurring in the sum, which is the DMI. And so because of the helicoidal nature of the DMI and the result of the tree, so you have a chirality for the skyrmions. This gives the topological protection, but so you have a charge that is +1 or -1, which may be a problem. So the current main problem actually is to be able to have a technological viability of the device. So the two main challenge is that to be able to work, to have a device that works without external magnetic fields and not at low temperature. Most of these systems will be able to stabilize skyrmions. It will be easier to stabilize skyrmions at low temperature, but of course, when you want a device, you want it to work at room temperature. And then the other challenge is because of this topological charge, when you apply a spin current, well, actually you will have this Skyrmions Hall effect that will arrive, which is nothing more than the equivalent of the Magnus law. So, for example, if you see here at the bottom, when you apply a spin current, the Skyrmions will not go in straight line, but it will deviate on one direction or the other, depending of its chirality. So this is where arise the spintronics based on antiferromagnetic system. There's several advantages. So first, when we are dealing with antiferromagnetism, you can go in the terrestrial frequency regime. The second one is that, well, you have a higher efficiency for transport mechanism. And so if we translate this for Skyrmions, well, this means that you will have a higher mobility for Skyrmions if they are propagating in an antiferromagnetic host. Since it's an antiferromagnetic material, you have no stray fields, and this means that there's no dipolar field or really low, small dipolar field, and this will mean that there will be less interaction from one Skyrmions to the neighbor Skyrmions, which is something that we want to achieve. And finally, in antiferromagnetic, you have a high exchange interaction, and this will allow you to have some coupled Skyrmions. When we are talking about coupled Skyrmions, is one Skyrmions in one lattice of the antiferromagnetic material, and one Skyrmions of the other lattice, and one will be coupled together. Why this is fundamental is to be able to get rid of this Skyrmions Hall effect. If you have one Skyrmions of one lattice, it has one chirality. When you apply a spin current, normally it will go on one direction. If you have two coupled Skyrmions, actually it will compensate the motion, the trajectory of the motion, and basically you will be able to have one entity, one coupled entity that will go straight. But the main problem to use antiferromagnetic materials, well, it's when we want to deal with the spin detection and control, either by current or magnetic field. And so one possible solution is to deal with ferrimagnetic materials, which on one hand will continue to have the advantage of antiferromagnetic spintronics, especially for the higher mobility and the coupling between Skyrmions. But since you have a ferrimagnetic, you still have a magnetic moment that you will be able to control and to detect. So here we pass to do two systems of multilayer. Both of them are synthetic cobalt gadolinium based system. Cobalt gadolinium will be the ferrimagnetic part, with platinum at the top and at the bottom. Both were deposited by magnetron sputtering, by co-deposition at room temperature. The difference is, one, we did some lateral confinement, so it was nanodisc, where we varied the diameter between 250 and 100 nanometer. In this case, the cobalt gadolinium was the alloy was 75 and 25, and the thickness was pretty thick, actually 1.8 nanometer. On the other side, we changed a little the composition of the alloy to be able to for AT20, but actually doesn't change so much about the properties. But here what we vary was the thickness of the cobalt gadolinium between 0.7 nanometer to 2.3 nanometer. So it was a two-way, either by lateral confinement or by varying the thickness that we play to be able to see if we first have a ferrimagnetic alignment of the cobalt gadolinium even at these low thickness, and then if we were able to stabilize some skyrmions in this materials, in these systems. So something that is really important, I will just introduce one technique, synchrotron technique that we use, which is X-ray magnetic circular Dichroism, which will be XMCD. And so it's based on Dichroism. So what it is the difference. We'll do the difference between X-ray absorption, but of different light polarization. And so before to be able to do some XMCD, you need to do first X-ray absorption spectroscopy, or XAS. It's a spectroscopy which is the main advantage is that it's element selective of the magnetic moments. So you're able to probe exactly one element in your system. Here we wanted to know what is the behavior of the cobalt lattice and what is the behavior of the gadolinium lattice. So XAF will be able to allows us to have the behavior of both of them. Then what is also it's possible here, it was not so much used, but to distinguish between the spin moment and the orbital moment. And for multilayers, here you don't need to have a large amount of materials, so 100 of monolayers. So even if we are at some nanometer thickness, we were able to use these techniques. So this is for X-ray absorption spectroscopy. So actually we are sending some X-ray, and then depending of the energy of the X-ray, actually you have the emission of a photoelectrons, and so basically you have the absorption of the X-ray. Now Dichroism, so it will be the difference between two light absorption, but two light absorption that are circularly polarized. So one is from the right polarization, the other is from the left polarization. You're also applying a magnetic field which is parallel to the X-ray beam, and so you will be able to probe the ferromagnetism of your sample. So here at the bottom you can see in black and in white, it's the absorption of the right and left polarization. And what is important in XMCD, it's actually the difference between the two. Here you can see we are working also well at the edge, one edge that is element specific. So we used these techniques, so done at the synchrotron here in Campinas, to know the magnetic coupling between the cobalt and the gadolinium. So we apply a magnetic field of 1 Tesla normal to the sample plane. And you can see here at the bottom, so for the cobalt, so we use the L3 edge of the cobalt and the M5 edge of the gadolinium. And so for the cobalt, if we are looking from the minus polarization passing to the plus polarization, we have a decrease of the signal at the L3 edge, and so we have a decrease of the signal, and so we know that actually we have a moment that is absorbing more from one side to the other. And at the opposite, when we are looking to the gadolinium results, we see that we are having now an increase of the signal of absorption. So looking to the XMCD results, so directly looking to the difference between the right, which is the plus, and the left, which is the minus circularly polarized X-ray. For the cobalt, we see, again, only looking to the L3 edge, we see that for the whole thickness that we are having, so even for 0.7 nanometer to the thicker, which is 2.3 nanometer, we have a negative signal. So if we have a negative XMCD, this means that the cobalt moment, it's parallel to the X-beam, and so it's parallel to the magnetic field that is applied. And for the gadolinium, for the M5 gadolinium, for all thickness again, but here we can see that we have a positive Dichroism, and so in this case, we have an anti-parallel alignment of the gadolinium lattice. So actually, at the end, we can know that we have an anti-parallel magnetic coupling between the cobalt and the gadolinium sublattice. And so we have a ferrimagnetic. We did this for the whole thickness, so between 0.7 nanometer and 2.3 nanometer. And you can see that the percentage of XMCD is increasing when increasing the thickness. This is only because increasing the thickness, you have more magnetic materials, and so the percentage of XMCD is increasing. But for the whole range of thickness, we always have an anti-parallel magnetic coupling between the two lattices. So even at 7 angstrom, we have two sublattices that are coupled. We also used this technique just to know, in function of temperature, what was occurring for the magnetic moment of each element. And so we did some measurement at 20K and at 100K. And for the cobalt, you can see that when we are increasing the temperature, so passing from 20 to 100 Kelvin, we are increasing the signal of XMCD, and so the magnetic moment of cobalt is increasing with the temperature. While we can see that for the gadolinium, actually we have the inverse. When we are increasing the temperature, we have a decrease of the XMCD signal. So when we are varying the temperature, one moment of the cobalt is increasing and one moment of the gadolinium is decreasing. And so we measured what is called the compensation temperature, which is the temperature for ferrimagnetic, while actually you still have an antiferromagnetic coupling between the two sublattices, but the magnetic moment of each element is equal. And so actually you don't have any magnetic moment. So we did some measurement at remanence after applying a 1 Tesla normal to the plane. And you can see in function of the temperature, so that even for 0.7 to 2.3 nanometer, we have each time a minimum of the magnetic moment. Just remember that all these measurements are done at remanence, so without applied field. So when we are increasing the temperature, the total moment magnetization is decreasing, it's reaching 0, and then it will increase again. And so at this minimum is the compensation temperature, which when we are increasing after 1.5 nanometer, when we are continuing to increase the thickness, actually you can see that this compensation temperature is increasing a lot, and then maybe we can even reach room temperature. Now looking to the magnetic behavior. So in function of the magnetic field, we look to the magnetization reversal of the sample by looking to the in-plane and out-of-plane magnetic curve. We can clearly see that we have an out-of-plane easy magnetization axis, so which is what we want. But for the smallest thickness, for 0.7 nanometer, we clearly have a different behavior of the out-of-plane magnetic curve, which now we have a square-like behavior. From this curve, we extract the saturation, magnetization, and the anisotropy field, because to be able to calculate the perpendicular magnetic anisotropy. Something that is important to point out, if you look to the saturation magnetization function of the thickness, we have a quadratic increase, while for the anisotropy field, actually, we have a linear decrease of this field when we are increasing the thickness. And so calculating the magnetic anisotropy, what we can see is that we have a linear decrease. So we have a stronger, in this system, we have a stronger influence of the anisotropy field than the magnetization saturation, the saturation magnetization. We also look to the magnetization remanence, and we can clearly see that actually we can divide the samples based on the thickness. For below 1.2 nanometer, we have a clear square-like curve with a high remanence, while increasing the thickness, we have a really low remanence. And so this has a coloration with to have a zero field skyrmions. When we have a high remanence, we are expecting maybe that we have skyrmions that are stabilized even at zero field. But to be able to know if we have skyrmion's texture or not, so we look to the magnetic texture directly to do some observation through magnetic force microscopy by MFM, which were performed at out-of-plane remanence and at room temperature. For all thickness above 1.5 nanometer, of course, we have the expected spin spirals. But here, actually, I was showing you the result for the unpatterned thin film. All the results are similar for the ones that are in nanodisk. But so for 1.8 nanometer, you have the expected spin spirals. But now if we are doing lateral confinement, so on the left you have when you have unpatterned, so spin spirals, and then patterning from disk of 100 nanometer to 200 nanometer. You can see below the microscopy, the electronic microscopy image, that for one single nanodisk at 100 micrometer diameter, you still have a spin spiral that is here, but reducing to 650 nanometer, actually you already have some skyrmions, but you have three skyrmions here, and then at 250 nanometer, actually you have one skyrmions in the middle of each nano island. So by doing this lateral confinement, we were able to stabilize single skyrmions, even in a host that actually normally there's we are in a spin spiral region. Now, so coming back when we have unpatterned thin film. So here the graph is the magnetization, the remanence magnetization function of the thickness. So in red is the thicker system that I show. So actually the spin spiral. You can see in the insert the periodicity of the spin spiral, which is increasing when we are decreasing the thickness. So function of the thickness, we can see that already we have some modification of the energy inside our system. So the periodicity is increasing until at 1.2, the spin texture actually it's more like a mixed. You don't have a clear spin spiral, and just if you just reduce a little more at 0.9 nanometer, actually you can see that you have a stabilization, a clearly stabilization of individual skyrmions. So we have a really abrupt transition between a spin spiral a little, and then below between 0.9 and 1.2 nanometer, stabilization of skyrmions. Remember that here we are at room temperature, and all this is at remanence. So this skyrmions, so we had in two samples at 0.9 nanometer and 0.7 nanometer. What is interesting to see is that the density of skyrmions is quite different. We have a higher density for the little, for the one that is a little thicker at 0.9 nanometer. When we are continuing to reduce the thickness, actually we have a lower density of skyrmions. These skyrmions, we are observing it from the surface, but actually remember that they are part of a coupled skyrmions. So one skyrmions on one direction of the cobalt sublattice, and there's the opposite in the formed by the gadolinium sublattice. So actually, through MFM, we were able to have an experimental detection of interfacial DMI interaction and in synthetic ferrimagnetic. These skyrmions, we look a little to this morphology. This is a part that is still ongoing. So the size of the skyrmions, it's quite large. They are quite large, so they are varying, and they are larger for a thinner thickness. So for 0.7 nanometer, remember that we had a lower density and we have larger skyrmions. And at 0.9 nanometer, we have a higher density and small skyrmions, but they are still pretty large, 210 nanometer. It's still pretty large. But something that is interesting to see is that they are not symmetric skyrmions. They shape, if we are doing some cross-section of the same skyrmions in different angle, actually we can see that they are asymmetric. Of course, when we were using lateral confinement in nanodisk, they were symmetric skyrmions. So in conclusion, the objective of the project was to observe, to really directly observe individual skyrmions in ferrimagnetic multilayers at room temperature and until no external magnetic field. So what we achieved here first, to be able to prove that we have an anti-parallel magnetic coupling even for ultra-thin cobalt gadolinium layer, so until 0.7 nanometer, cobalt gadolinium is a ferrimagnetic host, sorry. And in the two strategy that we used, either to have a lateral confinement or reduced thickness of the ferrimagnetic layer, we were able to stabilize some individual skyrmions. So thank you very much for attention. Again, I'm sorry for all the technical problems, but since I'm the first of the conference, I hope that I will be the only one in the conference that has some technical problems.
Thank you, Dr. Fanny. Yeah, hopefully this is a pretty good presentation to start off the conference. It was really interesting to hear you speak about the ferrimagnetic skyrmions. So right now we want to open up for questions. Does anyone have questions? So Dr. Fanny, we have a first question in the chat. So Alberto is asking if you have done XMCD at different fields. Is 1 Tesla the saturating field for CO and GD? Also, are there any beam lines in which you can perform nano XMCD and track the spatial dependence of the magnetization of each component?
First, we didn't perform XMCD at different field, only at 1 Tesla. You need to apply a field that is strong enough to be able to align your ferrimagnetic material without reaching the equivalent of the spin flop field to be, and so you have the two sublattices in the same direction. So actually, normally XMCD is made between 1,000 Ørsted to 1 Tesla to Tesla. There's no, you don't need to vary the field. You will not get any other information. And so it's not a saturation that you have. The other part was any beamlines in which you can perform nano XMCD. Yes, that was experiments that were done in the previous synchrotron that we have. In the new series that is at the end of the commissioning, we will be able to perform nano XMCD. So, for example, in 1 nano disk on 1 nano nano wire, for example, it will be possible. And so, yes, to be able to do to have a scan of the magnetization, yes, it will be possible.
Thank you. There is another question for you. It's off topic, but how can researchers in the nanoparticles for hypothermia application benefit from synchrotron?
Yes, no problem. Well, first, synchrotron is a really powerful setup technique. So mostly whatever you can do with X-ray in your own lab, but normally you will have a really noisy curve or so on. Then at the synchrotron you will be able to do. So, for example, for nanoparticles, you can to be able to probe the superficie, but you can do some X-ray absorption. You have the part that is, now I don't know if I'm going more technical, but XANES and EXAF, but basically it's all absorption technique. So you will be able to know everything about the electronics, the electronic structure, and so on, and so on. So maybe we can discuss more after, but there's several beamlines that are interesting, even for only diffraction, also X-ray diffraction, but with more signal.
I hope that answers Daniela's question.
Hi, Fanny. Sorry. I've just got one really quick question, but it's line 22. You showed us how you could sort of change the size of this platinum layer to confine and get some skyrmions. Did you try going smaller than 250 nanometers, and what did you see down there?
No, when this was done previously, actually, we only went to 250 nanometer, not down. It was just a technical problem of how they were produced. But actually, I didn't show it, not because it was, for example, nothing. It was that like no more skyrmions or so on. Monodomain or so on. It's just that unfortunately, we're not able to go down.
That's a shame. It'd be really cool.
And then there's the pandemic that went, and so.
So I guess we have run out of time for more questions, which is a shame. But Dr. Fanny, will you be joining us in Gathertown later, in a few hours' time? And maybe we can.
Yes. Normally, I will be there. Yes.
All right. Thank you. That would be great. So, if anyone else from the audience would like to talk more with Dr. Fanny about her really interesting work about ferrimagnetic spintronics, you could find her in Gathertown later in session 2. So, thank you, Dr. Fanny, for joining us today. We will